having looked into the properties of the masonry units and also some properties of the mortar and their combination, today we shall look into the masonry walls, some properties of the mortar, mortar selection, etc. So, general outline of our today's lecture would be mortar selection, followed by brickwork, some introduction to brickwork, something about the bonds therein, and then strength of brickwork we will introduce, right. So, we will introduce what is called basic compressive stress. Now, we discussed what are the types of mortar, some ideas about it, but there are certain things left out. We also tried to introduce in the last lecture about how strength of mortar and strength of brick combined affect the strength of masonry, but we will look into details of the same one today. Now, something more about the mortar. You see, we can always have some sort of mortar is, after all, it is nothing but a kind of cement and sand and water. So, it is essentially something follows from the concrete, but it is of much lower strength, and we have seen the properties required are totally different. Here the properties are, of course, strength is one of the property, but water retention is another major factor, shrinkage is another major factor, and workability in the sense that one should be able to apply it easily with trowel. Those are the properties required. So, but basically it is again the cement based material. So, cement, water, cement pozzolana water, lime cement or lime mortar, etc., cement lime mortar, that is what we discussed. Now, so we can use some additives like we do admixtures we use in concrete. Similarly, we can use some additive for mortars, and these additives are some waterproofing compound, then something like water reducing agent, you can improve the plasticity. I will come to the waterproofing compound, their air entraining agent, and also something like accelerators. Now, waterproofing compounds are those compounds which go into the mortar system and actually sort of improvise the pore structure there, such that the moisture vapor can move through it, but capillary water cannot move through it. So, it changes the surface tension characteristics of the pore, surface kind of a surface characteristics of the pores it change, such that the pores would act like almost like non-wetting liquid. Maybe we will have some discussion about this sometime later on when we discuss about some other properties, relevant properties like surface treatment, etc. So, when we discuss about them, damp proofing and surface treatment, sometime we might be discussing. So, essentially these waterproofing compounds are the one which will ensure that there is no liquid water penetrate into the mortar. Water reducing compounds are nothing but plasticizers, would improve the workability like we did in case of concrete, similar one. Air entraining agents, again they have similar sort of properties here, and accelerators are used so that it can quickly set. Remember, we said that quick setting, if it rather quick strength gain is important, so that you can lay the brick one layer over the other, you cannot delay too long, right. So, quick strength gain is important. One more important issue which you did not discuss much earlier is resistance to rain penetration. This is very important as far as walls and masonry structures are concerned. Now, rainwater can penetrate through this through the wall. Essentially, it can penetrate through the brick itself, and then it can penetrate through the mortar itself. But most importantly, it is the joint between brick and mortar through which water can penetrate. Normally, wind and rain follows together, what is called driving rain index. We may have some more discussion on this later in discussion with reference to dampness. So, it is actually driving wind and rain go to hand in hand together, and the wind driven rain penetrates into the wall. So, it is actually incident, or it impinges upon the wall, and when it impinges upon the wall, the water can be absorbed by the brick by capillary suction, That is what we have seen suction rate. So, capillary suction, it can be absorbed by the brick, and then it goes inside as it penetrates, and we mentioned that by the time the rain stops, it should not enter right onto the inner surface of the wall. The drying period, before drying period starts, rain moisture should not reach the inner surface of the wall. So, that is the issue of the brick. Porosity of the brick plays a it plays a role. Porosity of the mortar also plays a role. It should not move through the mortar, but most importantly, it is the joint. It is the joint which is most important. So, mortar it should be low porous, and the joint should be proper. So, it should have a good bond with the brickwork. If you have a good bond with the brickwork, there shouldn't be crack formation, and bond with the brickwork should be good, so that the moisture should not, rain penetration does not take place through the joints of the brick and mortar. This is important issue. The other important issue with reference to mortar is their durability. Durability, the two issues are very important, because as we shall see sometime later on, that sulfates in brick in the long run can cause expansion, particularly of parapet wall. You can see cracks at the parapet wall, because soluble sulfates in the bricks in due course of time, in the long run of service of the brick masonry, may leach out from the brick itself, the brick units itself, and then react with the mortar, resulting in expansion, and this may result in crack formation in mortar. So, sulfates presence in brick could be one of the reasons which can cause actually problem of durability in mortar. So, one has to use actually low porous mortar in such situation, and high strength mortar in fact. Salt crystallization. Now, if soluble salt crystallizes within the pores of the mortar, salt crystallization. We have talked about both of these issues in connection with durability of concrete. So, something similar happens here. So, salt crystallization taking place within within brick, leaching out salts. If they crystallizes, they can cause expansive pressure, and that can again result in durability problem of the mortar. So, these are the two issues related to durability and rain penetration. Other properties of mortar and additives we have discussed about. Now, let us see what happens, how mortar and brick together works with the masonry structure. We will come back to some mortar selection a little bit later, because this is based on this aspect. So, first of all, strength of masonry with strength of mortar. This diagram we have had a look earlier also. Now, we will have a look in more details into this. In fact, if you see, there are two diagrams. First of all, on this side is the strength of mortar, mortar strength, right, mortar strength, okay, on this axis, and this axis is the crushing strength of brickwork. So, this axis brickwork strength, in other words masonry strength. Now, if you go on increasing the strength of the mortar, the strength does not increase beyond this point, it does not increase beyond this point, and this is for a low strength brick. For a relatively higher strength brick, same thing happens. Initially, of course, as you go on increasing the strength of the mortar, there is an increase in the strength of the brickwork, but beyond a point there is hardly any increase in the strength of the brickwork, although strength of the mortar has increased. So, what do we see? Higher strength brick of course gives you higher strength of the brickwork, okay, and but increasing the strength of the mortar progressively does not increase the strength of the brickwork. So, it flattens down, This is one important issue. We looked back again, and then similar figure as far as bricks are concerned. Strength of the brickwork depends on unit strength as well, and as well as joints. So, that is what the idea. So, we test actually piers, we generally test the piers. Piers are tested, because you can't derive the strength of brickwork from the strength of the brick unit and mortar unit. I mean, I might individually test them, but we will see that the strength of the brickwork is far different than strength of either of them. That is what we have seen. The strength of the mortar, if we go on increasing, it does not proportionally increase, and we will see the ratios. In fact, it is much lower. the strength of the. So, what is tests are done on piers made out of brickwork themselves and not individual bricks and mortar and alone. I mean, these tests you do to find out the qualities of the mortar and qualities of the brick, but then strength of the brickwork is directly tested, piers are tested or prism tests are done. The Indian Standard Code of course allows you to do a kind of prism test. So, these are done, and we will see that strength of the brickwork is much lower than that of the unit and as well as of the mortar, okay, depending upon the situation. Some of this we will see today itself. Now, strength of the masonry. Now, this is, if you see, if this diagram, again we are repeating this diagram, but if you see, this axis is the strength of the brick, brick strength, brick strength, brick strength, brick strength. This axis is the strength of the pier, okay, different sizes of the pier. This is actually 9 inch by 9 inch, means 225 millimeter by 225 millimeter by 2.7 meter high pier, and this is something like 38 millimeter by 38 millimeter, 1.5 inch brick. This is 1.5 brick thick, this is just a 1 brick thick pier, 2.7 meter high, and this is also 2.7 meter high. All these are nearly about 2.5 to 2.7 meter high. This is also 1 brick, I mean 1.5 brick, this is 1.5 brick, this is 1.5 brick, and this is about 2 brick thick walls, I mean piers. Okay. So, when you test them, you can see as your strength of the brick increases, the strength of the pier does increase, but there is a point beyond which it really does not exist, I mean does not increase further. The mortar used here is of course the same mortar, and as the size increases, strength increases, lower the size, actually strength is less. So, the 2 points we note, one is that it does not increase monotonically, it increases then flattens down, and as the size increases, the strength also increases somewhat. So, brick pier strengths are something like this, brick pier strengths are something of this kind. A third diagram of the similar kind which we are repeating, we have seen it earlier also. This is the diagram which shows different mortars here. For example, if you look at it, this is 1:3 mortar. In fact, this is H1 mortar, the strongest mortar that we have. We mentioned H1 to L2. There are several types of mortar, H1, H2, M1, M2, M3, and L1 and L2. If you remember, if you recall the type of mortars when we were talking about. In fact, Indian Standard Code has Standard Code defines 26 mortars, different kind of mortars within this variety of H1 to H1, H2, M1, M2 and M3, L1 and L2. Now, this is the heaviest mortar, 1:3 cement sand mortar, no lime here, 1:2 cement sand mortar. Now, you have a same strength brick, uniform strength brick strength was same, but you changed only the mortar strength. So, this is the strongest mortar, and then this is the lightest, 1:3:12. So, it is actually 1 cement, 3 lime and 12. So, you can see it is much leaner mortar, and strength of the, this is the strength of the mortar, this is the strength of the brickwork. So, strength of the mortar to brickwork, they are nearly same here, like this is this percentage if you see, and here the strength of the mortar is much less, but still the strength of the brickwork is somewhat not much less, and as you go to a very weak mortar, the strength of the brickwork diminishes, but does not diminish very much. So, there is no point using unnecessarily very strong mortar. That is the idea we get. We get that idea that, right, that very strong mortar is possibly not necessary. Anyway, there is a corresponding mortar or an optimal mortar. So, if you look into now mortar selection, we will see that type of structure, right, type of structure, masonry unit strength, masonry unit type, whether it is brick, stone, etc., and their strength, the exposure condition, environment, etc., governs the mortar selection. The optimal mortar would be dependent on all these factors. It will depend on type of structure, the unit, masonry unit, because the issues are not only the strength of the brickwork, but the issues are also related to durability, range penetration, etc., etc. So, therefore, optimal mortar selection is based on this, and Indian Standard Code gives you some guideline, and as we have seen that high strength mortar is not really necessary. High strength mortar is not really necessary. I mean, very high strength. All the time you should not use 1:3 cement mortar, which is the strongest mortar with a strength of about 10 MPa. Optimal mortar is a choice. Choice is important, and this is given in a table in our code, and that is what we will look into. Now, this table looks like this. This table looks like this. You see, this table looks something like this. This table looks something like this. First of all, it gives you, I have just taken the part of the table, because full table it is impossible to take the full table. This is a very large table, but you can have the rough idea from which you can understand how this table is, and then of course choose accordingly. So, this is the situation, for example, foundation, external wall, internal wall, and reinforced brick masonry. This is reinforced brick masonry. So, for the various condition, unit type, this is not exhaustive, as I said. For foundation, this is not the only, you can have brick, stone, block, etc., and several other parts of the table. Actually, I have deliberately omitted, because I just wanted to explain the table. One can look back into the code and choose the appropriate mortar accordingly. Now, when you have brick, stone or blocks, this is block, this is means block, BRK stands for brick, stone or block for any types of unit. If it is a moist and sulphate environment, for heavily loaded, this is heavily loaded, heavy load, medium load, and this is lightly loaded structure. So, which is loaded heavily, use very strong mortars. So, it is an aggressive environment, you can see, very strong mortar, use strong mortar H1 and H2. In fact, as I said, 1 to 26 are the mortars, you know, and you use strong mortars. If it is lightly loaded, then use 3, and otherwise, you know, medium loaded, if you use 3, lightly loaded use 4 with plasticizers. P stands here for plasticizer. So, this is an example. In foundation, if you have moist condition, wet condition, the foundation is likely to be exposed in wet condition, and you have either brick, stone or block, and sulphate condition is expected there, then if it is heavily loaded, then use 1 to stronger mortar. If it is lightly loaded, use relatively less strong mortar with plasticizer, but you see, you are not using very weak mortar at all. You are using sufficiently strong mortar, because foundation would have to carry a significant amount of load. So, strength is required. If you lower it down, strength of the unit would, strength of the brickwork would definitely reduce down, but durability is a major issue here, and therefore you use a strong mortar. If you see the external wall, you know, case of external work and brick and stone, just another example I have picked up from the table, moderate condition, moderate environmental exposure condition, and there are 3 mortar selection for heavy load, heavily loaded, medium loaded and lightly loaded. 3 cases are shown. That is what is given in the table, and we have just reproduced the same thing. So, for moderate condition, it is suggested that you take 1 to 3 mortar or 4 to 6 mortar for medium loaded, and if it is lightly loaded, take 7 to 18 mortar. So, for external wall, this is what you can choose. Similarly, if you have internal walls which are not exposed to environment, which are not really exposed to environment, right, even normal condition, which you can call not very severe condition, normal condition you can call. In such situation, even for heavily loaded, you take 2 to 3 mortar, medium loaded 4 to 12, and you can go to the lightly loaded, you can go 13 to 26. So, this is the situation where you actually can use even weakest mortar, the most, you know, weakest mortar. See another situation, if you have early frost action in external or internal work, right, you are using any kind of units, then you can choose only 2, 3, 4, 2, 3 or 4 type of mortar. Recommended is for heavy loaded 2, for this is 3 and 4. Basically, the point is here, it should very strong mortar, possibly, I mean the mortar 1 H1 has not been selected here, instead 2 has been selected, because frost action means one thing, protection against the moisture. Very weak one you cannot take, it should be able to withstand the cycles, as many cycles as possible. And when you have reinforced brick work, you know, and you have exposure to moisture condition, you can't use for any kind of load, because in any case you are using reinforcement, means you expect a lot of load. So, when there is a lot of load, or even in especially in ductility, you might provide in case of seismic zones, reinforced concrete brickwork, reinforced brickwork are used for that purposes. Both it should be able to carry load also as well as resist horizontal loading. So, in such situation you use only mortar of the one type, that is the H1 mortar. So, that is what you use, one mortar. Now, let us see what these mortars are. 1, 2, 3 are H1 mortar, right. 1, 2, 3 are H1 mortar, 1 being 1:3 cement mortar with 10 MPa strength. In fact, the 2 is also H1 mortar with a strength of 7.5 MPa. 2 is also H1 mortar with strength of 7.5 MPa, right, and so on, so forth, right. And the L 26 is the actually L2 type of mortar with least strength. So, the combinations of these are given. I think I have given some of the combinations earlier. Let us see if I have something more here. 4 to 6 mortars are M1 mortars, 7 to 12 are M2 mortar, and 13 to 18 are M3 mortar. As you go down along this table, along the table which gives you the actually cement is less, sand you increase sand, and of course lime is also used, lime, or some cases is pozzolana lime sand mortar. So, that is what it is, right, that is what it is, the types of mortar. 19 to 23 are L1 mortar, 24 to 26 are L2 type of mortar. So, this is the mortar actually types of mortar, So, details one can look into the code and find out the relevant actual proportions of the mortar, actual proportions of the mortar. So, that is the idea, that is how we go about mortar selection. So, we select actually appropriate mortar, and that is it. Now, let us look into different kind of bonds that exist in brickwork. Now, we are interested in the brickwork itself. So, we have seen the mortar, we have seen the units, varieties of units, those are there. Let us see how do they join them. So, to join them, there are certain certain types of bond. Okay, first of all, let us look at this. Under load, the units shall act jointly, because basically the units I am joining together. So, they should act jointly, they should act together, right. Load must be transferred from one unit to the other. So, they should be bonded. So, this bonding is done by the joints, and there has to be a pattern, right. So, the pattern that are selected, the bonds between the bricks are selected such that it should be able to withstand the load fully. Now, one principle is, most important principle is that vertical cross joints in any course shall be staggered and should not be never nearer than quarter of a brick length from those in course below or above. Now, what are vertical joints? Supposing this is your brick, as we shall see, this is your brick, this is another brick, right, this is another brick, let us say in some form, and this is your mortar joint. What is being stated here is that next layer should not have the vertical joint here, next layer should not have the vertical. So, you are then in that case you are creating a vertical weak point, it can separate out very easily, because in this joints will be the weakest link. Mortar themselves are strong, brick themselves are also sufficiently strong, but the strength of the brickwork is much lower and is governed by actually the mortar. In fact, it is also governed by the kind of Poisson's ratio of the differential Poisson's ratio that exists, or differential modulus, nu by E, that is what we have seen. Because whenever you apply load to this sort of system, actually there will be movement along the transverse direction. Under vertical downward load, there will be movement along the transverse direction, and in any case one, depending upon the modulus of elasticity and the Poisson's ratio of Poisson's ratio divided by modulus of elasticity of the brick and the mortar themselves, one would possibly move more in the transverse direction compared to other. The one which moves less will actually induce a tensile stress into the other. So, that kind of behavior is here also, that kind of behavior takes place. So, therefore, we would not, joints tend to be weak. So, therefore, we would not like the joints to be in the same line. So, that is being said that most important, the vertical cross joints in any course shall be staggered. So, you can't have this should not be in the same line. And then if you have a joint, if you have one joint here and the joint in the next one is somewhere here, the minimum distance between these two is set to be 1/4, nothing less than 1/4 of a brick length from this course. So, there should be this distance should between this should be least 1/4 of the brick length. So, that is being suggested, and that is what ensures that actually failure plane does not exist at one point, and that is why different types of bonds are used. That is why different types of bonds are used. Okay. So, well, these are very conventional, because the people or the masons who work onto that, they really know it. It is not necessary that every time you have to tell what is the type of bond, but that is the idea behind having different types of bonds. They have specific purpose for having different types of bonds, as we shall discuss. So, there are several types of bond, English, Flemish, then stretcher and header bonds, and Quetta bond is adopted for these are the two common, but stretcher and header bonds are other types of bonds, and this bond is adopted for reinforced brick wall. This bond is adopted for reinforced brick wall. So, let us go to the next one and see the bond, English bond, let us say. Now, this has got alternate header and stretcher courses. The diagram will make it clear. Say this we call as header, and these are stretchers. So, this is header, this is stretchers. So, in this one, course A, let us say, and then this course B, course A, course B, course A. Now, A course has got headers along this direction. These are the stretchers here, right, perpendicular direction, another part of the wall, like wall goes like this, and this you can see is one brick thick wall. In fact, one brick thick wall, 2 bricks and jointed mortar, and this is the one brick thick wall. And the next course will have the stretcher here, next course will have stretchers here. So, that in in the elevation it looks like this. This is your joint, this is another joint, this is your joint, this is another joint, and this is the joint, this is another joint, and so on and so forth, and they are not, they are staggered actually. This one you will see that this is staggered. So, that is the idea is in case of English bond, this is called English bond. There is something called Flemish bond. Now, here headers and stretchers are used alternately. You can have 1.5 brick wall, you can have single Flemish bond, or you can have double Flemish bond. Let us see each of them. You can have single Flemish bond, or you can have double Flemish bond. Now, you see in this one it is something like this, in this one you have something like this, in this one you have something like this. You see, you have this course A, if you see, this is a stretcher, right. These are headers. Now, if you look at any one of them, header, then stretcher, header, stretcher, header, stretcher, and that is how it follows, right. So, this is 1.5 brick thick actually. There are 2 possibilities in case of 1.5 brick thick. It is called single Flemish and this is called double Flemish bond. So, you have header stretcher situations in this kind of bond, header stretcher situations, header stretcher, header stretcher, header stretcher, and so on and so forth, header stretcher, header stretchers, etc. As you can see. So, this is a kind of Flemish bond. This is semi Flemish bond, and again you see the vertical joints. Vertical joints are they are not in the same line. There is a gap between the two, and this gap is 1/4, more than 1/4 of the brick length. So, that is the idea about the types of bond and the Flemish bond that we are talking about. Now, you can have simply stretcher bond, say when we use in half brick partition wall, in this case you have just stretchers, just stretchers. This is in plan starts just stretchers, right, and this okay, course this is for a cavity wall, we will come to that, but you can see this is just stretcher, and you have stretchers. So, they are staggered, this first one is in this one you have to fill in it with a brick in the header, and stretcher, etc. right. Now, this is used for partition wall half brick thick, just not full brick length, half brick length. So, that is there, that is what is useful, and they are used also for cavity walls. So, this is a cavity in between, there is a cavity in between, right. There is a closer here, slate closer to jam actually. So, this is a cavity, this is the cavity, and this is the two like the headers in, stretchers. This is the stretchers in plan, as you can see. So, these are all stretchers and no headers here, no headers in this particular one. If we go to the other one, this is called header bonds, and this is just all headers used mainly for carved wall. And you have of course, you can see that this is just the headers. First one should be something like this. So, it would look something like this. See, this is the header, this is the header, this is header, and this is how it looks like. So, with sort of lap length, half brick lap length, exactly at the center these joints are, and in the previous case also it was in the same case, same type, because you had joints just at the center. So, you have a lapping length of half brick. So, this is the half brick length, this is another half exactly at the center, and that is how you stagger it. So, that is how you have the bonds which ensure that there is no vertical joints are formed together. That is the basic idea, and this one may not bother too much about it, but we must understand what are the basis of this one. We do not want vertical joints along the same direction. I mean, they should not create a weak point. So, that is the idea. So, one has to follow the standard bonds. There is not much to be done about it, standard pattern of the bonds, and not really big engineering goes into it. So, that is it. Now, when you have reinforced brick masonry, then you use a bond called Quetta bond for 1.5 brick reinforced brick wall, and this is how it looks like. In this case, you have the reinforcement here, and the mortar goes in here, reinforcement, mortar, and therefore, this has to have the gap. So, this is this is a stretcher, header, etc., stretcher and the header, and in between you have a gap and where the reinforcement goes. So, this is the reinforcement bar, usually is used in places where you want slightly taller building, maybe taller, not just 3 or 4 stories, maybe 5, 6 stories construction you got to have. This is reinforced brick masonry can be used, and especially where you have seismic considerations are there, the earthquake resistant structures you need in load bearing masonry, there you might be using this. Strength required is more. So, usually it is nothing less than 1.5 brick wall. So, 1.5 brick reinforced brick wall where you use this, where you use this kind of bond. So, this is all about the bonds. Now, let us come to the wall strengths. See, we assume that in case of, if you have a brick work, the load will be transferred. If I have a point load onto a brick wall, the load will be transferred through an angle of 30 degree. Vertical, it is transferred through an angle of 30 degree, right? Vertical load is angle of dispersion of the load, that means it will disperse 30 degree angles. These are 30 degree angles. So, this is what we assume, concentrated load, and accordingly we calculate out the load, etc., etc. Okay. The second issue, important issue, is the strength of masonry depends upon several factors: slenderness, strength of masonry wall. First is of course the strength of brick work itself. That is something we have discussed about it, but the wall, the load it can carry would depend upon the slenderness of the wall. Okay. Now, if we can remember the slenderness, it is the thickness, minimum thickness. So, length by effective length divided by the thickness, that is what is the slenderness of the wall. So, the load it can carry not only depends upon the strength of the masonry itself, but it also depends upon several other factors, the most important being slenderness, because as you know, wall is a vertical member, and such vertical members are mostly subjected to compressive load, gravity load, compressive load. Usually, if you have undergone a course on reinforced concrete design or similar other design, you would know that members like beam, they take the load by bending. They take the load, they respond to the load by bending, and whereby the top portion compresses, bottom actually, if it is a simply supported system, or in any case flexural members, normally as we have seen earlier, that the top portion would shorten and bottom will actually elongate, and thereby that is how it actually resists the load. Direct tension is usually unusual except for members like very thin members, steel structures or cables and similar sort of cases, or in trusses you might have members in direct tension, and that is a very efficient way of, more efficient way of taking the load, because whole cross section will be acting under the load. But when it comes to compression, compression induces what is known as buckling. Compression induces what is known as buckling. If you remember, if for example, if you have a stick, thin stick, and you try to put pressure onto it, it bends like this. Although the material failure may not have taken, but it bends. So this bending can cause failure due to buckling. So compression member, it buckles, it bends under the axial load itself, it bends, and that's buckling can result in failure. Now there is something in case of structural, I mean strength of material, you would have studied. There is something called Euler's buckling load, Euler's buckling load, and it is seen that this buckling, the stress which it can, critical stress associated with the buckling, is inversely proportional to L by R, and this L by R is nothing but slenderness ratio. So in case of brickwork, we define slenderness ratio by effective length by T. Why effective length? Because it will depend upon the fixity of the end. Supposing the end is totally fixed, then if the end is totally fixed, then this portion will not be available for buckling. It will buckle, it will buckle between this length. If it is, let us say, simply hinged between the two, then full length will be available for buckling, because it will depend upon what is the kind of restraint is available here. If this place is fully restrained, if these places are fully restrained like this, then no buckling can take place here. This will have 0 rotation, this will have 0 rotation, and effective length will be smaller than the overall length. How much it is, we will look into in details. So we define the slenderness ratio in case of slenderness, we define in terms of effective length divided by the thickness of the wall, and as we shall see later on in the next class possibly, or in some other subsequent lecture, that it can buckle in both, the buckling can take place against about a horizontal axis. For example, wall can buckle in this plane, and also it can buckle about a vertical axis. That means in plan it can take a bent shape like this due to buckling. So this is an important issue, and this governs the strength or load carrying capacity of the wall. Strength is one thing, but this is other issue. Second issue is that loads are rarely applied, loads are rarely applied axially. Quite often, if this is my thickness of the wall, T, load, instead of load being here, effective load may be somewhere there. So this is the eccentricity, So load might be applied not at the center of the wall. Why? Because, for example, something coming, a slab coming from the other side, let us say in load bearing wall, and only from one side, let us say. So the slab load would be transferred not exactly at the center. In fact, this portion may be, if you look at the distribution of the load from the wall, it may be something like this. I mean, load from the slab to the wall, it may be something like this. So net location, effective location, or the center of action of the force, that is the load that is coming from the slab, may not be exactly located at the center of the wall itself. That can result in kind of eccentricity. Or if I have slabs on both the sides, one has got larger span, other has got smaller span. So that kind of various situations should be there where eccentricity may be induced, because the load is not acting right onto the center of the wall. And when it is not acting onto the center of the wall, this eccentricity induces a kind of moment. And let us understand that brick masonry really cannot take tension. It is a material like concrete, it is a brittle material, and such material cannot take tension. That is what we have seen. And that is why, earlier days also, although brick masonry was there for very long time, as we said historically, mostly arches or domes were constructed out of them. You could not have flat slab like construction. in brick masonry. So, that is why, because it can't take tension. So, the bending member you can't make out of brick masonry, it can't take tension. So, we assume that practically, although it can take small tension, practically we assume that it does not take tension. Now, when you have a moment induced due to the eccentricity, there will be some amount of tension coming onto the, it may come depending upon what is the eccentricity, there can be tension coming into the material, and again buckling and eccentricity together, they may act together, because when something is bending vertically due to buckling, and if you have eccentricity, this will further cause this movement. So, all these issues together, eccentricity, slenderness, both of them play a role in the load carrying capacity of the member or the brick wall, right. Then there are issues related to area of the wall and shape of the unit, and area are related to the wall. So, these are some other factors which affect the how area works. As we have seen that smaller the like one of the figures we have seen, that 1 brick thick wall could carry less load compared to the stresses would be, the area has some relationship, actually area has got some relationship. Of course, the stresses, one has to see the stresses, not simply the load. If you make it thicker, it will carry definitely more load, but stresses also are observed, that area has got some effect. Why it is, we will discuss this sometime later on in details, but area has got some role. Also the shape of the unit has got some role as far as the load carrying capacity is concerned. This can be quickly understood, although we will again discuss this in some more details. Supposing you have got smaller units, then what will happen? If I have smaller units, more number of joints would be there. If you have larger units, possibly less number of joints. So, this has got some sort of effect. Now, more number of joints means strength would tend to be smaller, it would tend to be weaker compared to where it is less number of joints, because we have seen it is the joints which actually plays a major role as far as strength of the masonry is concerned. So, all these factors actually affect the strength of brick masonry. Besides of course the unit strength and masonry strength, we will look into these issues somewhat later on, but let us look at these issues first, that is masonry strength, unit strength and masonry strength. So, how does one does? You see, this brick masonry design has by and large been not well understood. Behavior of brick masonry not well understood. In fact, behavior of steel is very well understood, because it is a factory produced material, very well behaved material, and in a course of materials and construction we devote, or in any case of a material, we devote very little time to steel, because it is a well behaved material, its sustained behavior is very well known. When it comes to concrete, we know some of its behavior, but then we make it ourselves, it is not necessarily factory produced material. So, we devote some more time and to understand both concrete. Well, masonry is more even relatively not so well understood like concrete, or possibly even less understood than concrete. So, it is based on mostly empiricity again, and therefore, what does code or similar sort of code or similar documents do, or guidelines for design they do? They first give you a strength based on unit strength and masonry strength, and that we call as basic compressive strength, permissible stress. We are talking of the stress that is permissible on the material. You know the load, you can calculate out the stresses, because load and eccentricity known on a wall, you can calculate out how much will be the stresses. Now, this stress must be less than the permissible stress. It is like an working stress method of design. In case of plain brick masonry, we design it based on a working stress method, simply load divided by area or eccentricity, you calculate out what is the load and stresses, and this stress must be less than the permissible stress. Now, this permissible stresses, of course, there is a certain amount of factor of safety involved in all of them, and permissible stresses comprises of first the basic compressive strength. Now, basic compressive stress, you can say permissible stress, basic compressive strength, or basic compressive permissible stress at 28 days, and this depends upon the unit strength and masonry strength. Now, once you know this basic compressive strength or basic compressive stress that is permissible, which is depending upon the crushing strength of masonry and the grades of mortar, This is of course valid for slenderness ratio less than 6, the eccentricity being 0, and the height to width ratio of the unit is less than equals to 0.75. The shape is not, this is for a, so for a given shape, given eccentricity, given shape, given eccentricity and given slenderness ratio, this is given. Then you have certain multiplying factor related to this one, slenderness ratio, eccentricity, etc., area reduction factor, and then shape factor, etc., etc. So you have some multiplying factor, and finally by multiplying by this factor you come to the permissible stresses. So first you find out the basic permissible compressive stress based on the strength of the masonry and strength of the mortar, and then this is valid for slenderness ratio 6, eccentricity equals to 0, and height to width ratio of 0.75. Once you have known this, then you can calculate out the rest. So let us today look into the basic compressive stress, and the other ones we will look into later on. So look at basic compressive stress, permissible stress. Well, again there is a large table given in the code, there is a large table given in the code, and I have picked up only a small portion of the code just to show you how the table looks like, because one can find out how much will be the value, one can find out how much will be the value from the like table. So table is readily available, but just we want to, for the understanding, I have picked up a small portion of the table. So you can see that in this one the mortar, different types of mortars are given, and basic compressive stress, permissible stress for various unit strength starting from 3.5 to 40 MPa. These are all in MPa. These are all in MPa. These are all in MPa. This is all in MPa. So MPa 3.5. So very weak unit strength to highest strength. That's what I have just picked up the left hand corner of the table, and here again I have picked up only 5 mortars out of the 7 mortars. If you remember, I said there are something like H1, H2 mortar, then M1, M2 and M3 mortar, and L1 and L2 mortar. So all makes, I have just omitted 2 of them, because we want to understand how this table is rather than looking at the table, because you can always look at the table in the code and find out the values as and when you require. So let us see for the weakest mortar, as my this is the strongest mortar, and the mortar strength reduces along this direction. Now this mortar has got a strength of 10 MPa, minimum strength of 10 MPa at 28 day strength, and unit strength is 3.5. Since mortar strength is 10, this is about 8.35. When mortar strength and the unit strength is nearly same, we have seen the strength is as good as the mortar strength itself. When strength of the mortar strength, for mortar strength for strong mortar strength is as good as the brickwork strength is as good as the mortar strength. So mortar strength governs it significantly. So whenever, even if you have a weak brickwork, the mortar strength seems to controlling it, and this is about 8.35 MPa, much higher than this, because this has got a strength of 10 MPa. This has got a strength of nearly about same, this is showing same strength, but when it comes to a weak mortar, it quickly diminishes, and in the weakest mortar it is about 0.25 MPa. When you have a 10 strength is much higher. Now it is similar, you have 1 MPa strength here, this is 0.96 and 0.81, 67, 53, etc., etc. When you have 40 MPa, so by and large this is the case. This is the case you have much less strength of the brickwork, much strength, less strength, lower strength of the brickwork compared to actually mortar strength. So using this particular table, one can select the basic compressive stress, permissible stress in the brickwork, and then multiply by the correction factors, that is the correction factors, namely the slenderness ratio and what is called stress reduction factor. The stress reduction factor is based on slenderness ratio and eccentricity, and then you have something called area reduction factor and the shape factor. So this multiplication factor one can use and find out what is the permissible stress in the brickwork. So far in this case class we have looked into the basic compressive stress. In the next class we will concentrate ourselves onto the these factors, those are there, and how one calculates out the overall permissible stress in the brick. Although design is not really an aspect of this course, design is fairly simple once you know, because the design would be dependent upon how do you calculate out the load. So first find out the load, and load is found out, you would have done similar courses in structural analysis and design, where from you know how to calculate the load that will come onto a wall. That means how much, I mean, for example, you can know, you know how to calculate out the load onto a beam in a frame structure from the slab, how the load, you know, how much load is contributed by the slab to a beam. In the similar manner, one can find out how much load is contributed by the slab to a wall. So once you know the load that come to the wall, then simply load divided by the area plus, if there is an moment, so moment divided by z, you know, that would give the stress, plus minus m by z, that will give you the stress. And once you know the stress, this stress must be lower than the it must be lower than the permissible stresses in the brickwork. So we in this course, of course, we will look into, in this discussion in the next lecture, we will just tell you how to find out the permissible stresses. Load calculation etc. could be part of some other structural analysis and design course, and they go in the same manner. So we will not look into the full design, because that is not part, it involves so many things. So part of the construction issues, you know, how to calculate out the permissible stress, that is what we will look into. Anyway, so coming back to the summary of this discussion, we have seen some issues related to mortar selection. Mortar selection, how do you select the mortar, we have understood, and I have given you the table from which you can find out which mortar should be used in which situation. Although only part of the table I have given, but if you look at the IS 1905, IS 1905 is the code which deals with IS 1905. This is the code which deals with this brick masonry design, and also special publication 20, which is the commentary on the above code. This gives you the details of masonry design for unreinforced brick masonry. So one can look into this commentary and this together, both for understanding purpose as well as for the tables that I have mentioned. So I have given you the tables, it's part of it, but overall table is available from which you can find out how to select, I mean which mortar to select in a given condition. And then we have looked into different types of bonds. Now these are basically ideas of construction practices, and this has been so standardized, does not really require much much you know, there is not much to be really memorized about it, but what you know is that vertical joints should not come in the same line, that is the whole idea. Then we have given you the concepts of basic compressive stress, basic compressive, you know, permissible basic compressive stress or basic compressive strength, which is which we find out from the strength of the masonry and the strength of the unit, I mean strength of the mortar. So for corresponding mortar, I mean for a given strength of the unit and mortar, we can find out what is the strength, and this is to be multiplied with stress reduction factor, slenderness, etc. So due to slenderness and eccentricity, it has to be multiplied with area reduction factor and shape factor to come to the permissible stresses in brickwork. In the next class, we will look into those two issues, effect of slenderness and eccentricity on permissible stresses, effect of area and shape on the permissible stresses in the brickwork. I think with this we conclude our discussion on the you know, discussion of first part of discussion onto the walls, and the second part will continue, I mean walls will continue, second part of course related to strength in the next one. Thank you.